All right, so somebody's going to give me some intuition for 2.4, number 15 here. What do you got?
Uh, I was thinking that part A is true.
Okay, why are we thinking that part A is true?
I didn't expect you to have me explain myself. It. I was thinking of the of kind of like the row picture multiplication, and in my head it just like working through a couple like just working through it. It just kind of seemed like it turned out that they had to be square.
Okay, I'm kind of with that. That seems legit. Um, Let me think. So, what
Bro,
if A was m by n, right? And then if a square is defined, what does that mean I can do?
That means you can multiply a by itself.
Okay, so that means that a m by n is defined, right? This works basically, right? A squared is defined really means that a m by n times a m by n works, right? Now, what's the thing that's required for matrix multiplication to work?
the n and m should be equal.
Yeah, these two dimensions have to match, right? Because I need to pick up the columns of A, turn them sideways, and drop them onto the rows of A. I need to be able to do the dot product between a row and a column. So they need to have the same number of things in them. You guys see that? So the fact that this works means that m equals n, and that means that A has to be square. You guys all cool writing that sentence down a little better than I did?
Yeah. I just wish I could explain it in a way that makes sense other than, well, I looked at it in my head.
That's okay. I mean, that's how proofs start. Like really, a good proof start says, I looked at it in my head and found that it was true. Then the writing it down becomes a different thing, and sometimes you'll find that your intuition has betrayed you. But oftentimes it's pretty good. So should start there. It's okay. All right. So let's see. If A and B and A are defined, then A and B are squared. Is that true?
I don't think so.
Yes.
Oh,
Karen
Karen
says
says
yes. You guys say no.
Karen says yes, so I believe
I
Karen.
don't know.
I was.
It could be yes.
Oh shit.
I was
Pistols at dawn, huh?
In my head I was thinking again row multiplication, and if we have a 1 by 3 and a 3 by 1, if we pick it up, twist it sideways, then you could still do that row multiplication.
Let's see. So if we had 1 by 3 and 3 by 1, then these numbers match. And so we'd get something, but it's 1 by 1, right? And if we did it the other way, we'd get something. And how big is that something?
It's 3 by 3. So Karan is not always right.
Karen is not always right. While Karen may always be right about algebra, it turns out that linear algebra is a slightly different beast. Bummer. No, so these things are cool because this one, you guys recognize what that actually is? What's a 1 by 1 matrix?
a scalar.
Yeah, that's a scalar, right? So this is taking two vectors, right? One's a row vector and the other one's a column vector. You take two vectors and get a scalar out of it, right? Yay? What's that? It's a special kind of product that starts with a D. Good. It's the dot product, which you all know and love. Right?
I think it's the fact that you like set it up to be this huge big reveal, and then all of us are like, it can't be that.
I know. Yeah, it's just a dot product. So if you have a row vector times a column vector, you get a scalar. That's a dot product. This other thing, where you get a 3 by 3 matrix, that's called an outer product. It is actually a thing that we'll have occasion to fiddle with for just a hot minute later. So this is false. And our counterexample is vectors. Are you with me on that?
Yeah.
Okay. If A and B and B and A are defined, then A and B and A are square.
I was thinking yes on this one.
Yeah, that one feels true, right?
Yep.
So if A and B are defined, so if I've got A m by n and B, I don't know, I need new letters. Not y by z, I guess. Right? So if A and B is defined, that means that n has to be y. Right? If B and A is defined, that means what? That'd be this one. What does that one give you?
Z equals M.
Okay, that'll tell you that Z has to be M. And so, okay, so then they have to be not the same size, right? But they have to have the same dimensions, just flipped. You guys with me on that? So that would mean that A m by n and B is n by m. So the results AB is going to be, well, that one's going to be m by m, and BA is going to be n by n. That was a shit, like, this is crappy writing, but that's the right idea for the proof. You guys good with that?
Yeah.
Okay. How about if AB is B, then A is I?
Definitely not.
Why not?
B could be the zero vector, and also we found a matrix that multiplies by itself to give itself today. So it's wrong in several ways.
Yeah, perfect. All of that is exactly right. Yep. Yeah. So, false. Counterexample is, I guess, my take A to equal B to equal this guy.
Or even the 1, 2, 0, 0 vector or matrix.
Oh, yep. That one also works.
Mm-hmm.
Any questions on that? That seems real weird, right? The moral of that, which is important, so I'm gonna stress it here. This, oops. The like moral implication of this statement is you can't divide by matrices. You guys see that? That would be kind of, you would kind of look at this and you'd say, okay, well, I'll just cancel the B's out of this thing, right? And then I'll have A equals I. Why can't you divide by matrices? Like, why can't I divide by matrices? What is a matrix at the bottom? All the way down near the sheep. what is a matrix? Other than a box filled with numbers.
Kind of like a vector.
Okay, that's fair. Yeah, a vector is certainly a matrix. You couldn't hope to divide by a vector, right? Okay, that would be actually really good intuition. My inclination is to tell you that a matrix is a function, and not all functions have inverses. So when you're trying to divide here, what you're really trying to do is you're trying to apply an inverse function, and if there isn't one, then you're kind of shit out of luck.
For this one, I was. Oh, wait, never mind. You just talked about how if it doesn't have an inverse. Never mind.
Yeah, in the case that the matrix B has an inverse, then this implication is true-ish.
Well, I was thinking that A could be some matrix times its inverse. Like A could be make up two different matrices multiplied together to make I.
Yeah, so in the case that I had a B inverse, what I could do is multiply from the right here by B inverse. And that would give me something a little bit strange. But A times B is B, right? Then I'm going to multiply from the right by B inverse. So that would give me B inverse is B inverse. You guys see that? So if B is invertible, you guys with me on that?
Mm-hmm.
And then these guys, B and B inverse, those are the identity matrix, right? So we could say, okay, so then A is I, because this thing is the identity matrix and A times the identity. Okay, let me maybe say that as right. And this is really because B inverse is the identity matrix. And so if B is invertible, that's true. So then I would have this, and then A times the identity matrix is A. So I would have, then I would get that A is the identity matrix. So in the case that B was invertible, you could do this. But matrices are not necessarily invertible. In fact, a great many of the ones we deal with in the course won't be. Does that kind of make sense? Okay, I'm going to assume it does.